This set of demonstrations illustrates the interoperability that is possible between the MillSoft Windmill Engineering Analysis Suite, the Command Center AMR system provided by Hunt Technologies, and QEI's Scada system using multi-speak real-time interfaces. While the load allocation feature in Windmill is a very powerful tool for estimating the distribution of load on the system, it can only be as accurate as the billing data we supply it. The need to compensate for diversity in the load distribution by choosing some appropriate coincidence factor introduces another possible source of inaccuracy. In the past, we've been willing to live with the uncertainties involved in representing the load on the system. But recent advances in automated meter reading systems and Scada systems now allow us to paint a much more accurate picture of system load. This, in turn, can lead to more accurate engineering analysis results. The relatively new breakthrough in AMR systems is the ability to obtain a coincident demand reading from every meter on the system. Rather than simply reading the peak demand for the day or the total monthly kilowatt hours, AMR systems can potentially give us a snapshot of the kW demand on every meter in the system at a single instant. This eliminates the need to compensate for diversity in the load distribution because we're guaranteed that the demand is 100% coincidental. Recent developments in the multi-speak specification have allowed us to read this kW demand data directly from the AMR system using a multi-speak real-time interface. This particular demonstration shows how kW demand data and interruption data can be passed from Hunt's Command Center to Windmill using web services. It is important to notice that the Windmill model we are using for the demonstration is a detailed model, meaning that the electrical system is modeled all the way to the consumer. Additionally, you will notice that each consumer has already been assigned a meter number that links it to the corresponding AMR endpoint in Command Centers. These meter numbers must be properly mapped to the consumers in the Windmill model in order for the AMR interface to work. Notice that Windmill is in load allocation mode and that all of the consumers in the model are colored black, indicating that there is not yet any load on any of the consumers. To demonstrate how Windmill can read the kW demand for these consumers directly from Hunt's Command Center, we will open the AMR Data Importer by choosing Real-Time AMR Data Importer from the main menu in Windmill. The AMR Data Importer has a setup page for configuring the connection to the AMR system and an options page for specifying which data you would like to request and what you'd like to do with it. Notice on the options page that there are three main types of data that Windmill can read from the AMR system: AMR vendor tags, outage events, and meter readings. Importing the AMR vendor tags will allow Windmill to stay up to date with regard to which consumers are associated with which AMR endpoints. If Import Outage Events is selected, Windmill will request all the momentary interruption events and sustained outage events recorded by the AMR system within the chosen date range. If Import AMR Meter Readings is selected, Windmill will request all kW, kVAR, kilowatt hour, and signal strength data that were recorded by the AMR system on the chosen date. Notice that when meter readings are imported, several options are available to determine what to do with the imported readings. The load data may be imported directly into the calculated load fields, or imported into a billing load group to await a future load allocation operation. While some meters are capable of reading kVAR values, most are not. If the AMR system does not report kVAR for a consumer, the user has the option to either assume some power factor or leave the existing power factor unchanged. Once all options are appropriately set, we click the Run button to begin the import. What is happening here is that Windmill is calling one or more web service methods on the AMR system's web server. There are no batch files being transferred here, and no user-initiated action is required on the AMR side of things in order to transfer the data. The AMR system is simply running a web server that listens for requests for data. When it receives a request from Windmill over the network, the AMR system automatically and immediately responds with the requested data, which are then stored and displayed in Windmill. Now that the import has finished, we'll take a look at the data we received. First of all, we notice that we received one warning message after the completion of the import process. The warning message is telling us that the AMR system disagrees with the Windmill model about the phasing of consumer 6402010. The AMR system is telling us that the consumer should be A phase, but the consumer is modeled in Windmill as B phase. A quick glance at the consumer in question reveals the reason for the discrepancy. The most likely explanation in this case is that whoever built the Windmill model mistakenly connected this consumer to the wrong transformer. A quick change feed operation corrects the problem. So the AMR interface has actually allowed us to identify and correct modeling problems in Windmill. Now let's take a look at all that data we just imported from the AMR system. We'll change back to load allocation mode to show that many of the consumers are no longer colored black, indicating that they now have load applied. The load on each of these consumers was measured by the AMR system at a single moment in time, so there's no need to compensate for diversity. Notice that we have chosen to default all power factors to 90%. This is because we began the demo with no load on the model. In practice, if the power factors on your model are already correct, you would want to choose the option to keep the existing power factors unchanged when you import new kW demand readings. Notice the Consumer tab displays some imported information as well. The AMR vendor field displays the type of meter associated with this consumer. This is useful, for instance, for distinguishing which hunt meters are TS1 and which are TS2. The kW read time gives the date and time at which the kW usage occurred. If the AMR system has been set to perform a coincident demand reading, this time should be the same for every meter. However, if you're using a system that can only report the peak demand for each meter, this system will indicate the time of day at which each consumer's usage peaked. The momentary interruptions and sustained outages field show the total number of outage events occurring between September 1st and September 13th, the date range we requested in the AMR data importer. If the AMR system supports signal strength measurements, this will be displayed on the page as well. The signal strength is imported along with the kW demand readings and can be used to help predict potential problems on the electrical system. Windmill can also display the imported data graphically via the Color by Custom mode, which allows us to color elements based on certain criteria. Here we have chosen to color elements based on the number of sustained outages reported by the AMR system. You can see here that the AMR system reported one sustained outage for the consumers colored red and two sustained outages for the consumers colored blue. We can also create user-defined color modes to show the locations of momentary interruptions. And the same can be done with signal strength measurements. Now that we've demonstrated the AMR interface, we'll show Windmill interfacing with QEI's Scada system. Throwing a Scada system into this mix allows us to take another step down the path towards accurate load modeling. Because a Scada system can supply up to the second readings of phase currents at the feeder breakers, we can run Windmill's load allocation analysis at any time of the day using the actual phase currents that are being measured at the feeder at that instant. The load allocation analysis will use the load distribution data obtained from the AMR system the previous day and either proportionally increase or decrease the modeled demand at the consumers depending on whether the feeder currents are higher or lower right now than they were at the time the load snapshot was taken. Additionally, a Scada system can provide the engineer with data such as fault currents and device statuses, that further enhance his ability to understand what is happening on the system right now. This particular interface with QEI is a TCP sockets-based interface, but Windmill also supports web services interfaces with other Scada systems using the Multispeak 3 specification. In order to read Scada data, it is first necessary to tell Windmill which Scada points should be associated with which Windmill circuit elements. To perform this mapping, it is helpful to request a list of Scada points from the Scada system by choosing Get Real-Time Scada Points from the Real-Time menu. The Scada system uses the Multispeak real-time interface to transmit this list of Scada points. If we open the Circuit Element Editor for the circuit breaker, we now see a Scada page that allows us to assign one or more of these Scada points to various fields associated with this device. There is a drag-and-drop interface that facilitates this mapping. Once the Scada points have been assigned to certain elements, the link is saved, so this mapping only has to be performed once. There is a fault current page for assigning fault current Scada points so that Windmill can read the latest fault currents from the Scada system. After reading the fault currents, you may click the Run Fault Locator button, which will immediately invoke Windmill's fault locator and automatically enter the fault currents that were just read from the Scada system. There is also a device status page that allows Windmill to ask the Scada system whether this device is currently open or closed. And finally, there is a general analogs page that can be used to assign any other types of Scada data that you might be interested in seeing. This Multispeak interface with Scada is probably the most useful in the process of load allocation. The ability to read all feeder currents on the system and then immediately use those feeder currents to perform a load allocation is invaluable. The first step in making this happen is to assign the Scada points for the feeder currents to the appropriate load allocation points in Windmill. Once again, after this mapping has been performed, the links are saved and will not need to be performed again. Once all of the Scada points have been assigned to the appropriate load allocation control points, clicking the Get Real-Time Scada button will cause the Scada system to populate this grid with the actual currents measured at the feeders. It has always been possible to perform this task by manually entering the feeder currents, but this new Multispeak interface with the Scada system greatly reduces the burden on the user imposed by having to move back and forth between different systems, manually copying large amounts of data. Now if we run a load allocation analysis, the loads we imported from the AMR system earlier will be adjusted to compensate for this actual demand measured at the feeder. In this case, the load on each consumer on the feeder has been proportionally increased by the same factor, because the total demand on the feeder happens to be greater right now than it was at the time the AMR system took the original load snapshot. So the combination of these AMR and Scada Multispeak interfaces allows us to paint a much more accurate picture of the system load than using either system in isolation. We use the AMR interface to obtain the relative distribution of demand, and we use the Scada interface to obtain the absolute quantity of demand. The end result, of course, is more accurate engineering analysis results.